Hey, hello everybody, what's up? I hope you guys have a wonderful couple weeks. It's been a couple weeks since I've started doing this. I've been busy. Today we have the Data Science Institute and the Association of Computer Engineers with us today. Thank you guys for coming. That was great. That's great. Hold on. I got this. Thank you guys for coming. Thank you guys for watching. I appreciate it. Any viewers count? Let's go. I have a couple minutes while I wait for this to happen. If you guys have any questions, hit them up in chat. I got Brian right next to me. Brian, say hello. Hello. He's looking at chat, so if you guys have any questions while I'm doing this, you can go by and see. All the links you'll need for this are in the description. I suggest you use this link because, I tried it out. All you have to do is just click on this link, go to edit, and you can go through here. You can press, to run a cell, this is just a normal notebook. To run a cell, just click the play button, or you can press shift and tab at the same time and it will run a cell. But today I'm going to be using Colab. I'm going to be starting from a blank slate because I hear a lot of you guys are going to be following along, and I appreciate that. So I'm going to do it at a pace where you can follow along. Today we're going to start out with a bit of slides. I'm going to talk a bit about our sponsors today. We have the Association of Computer Engineers, ACE, and the Data Science and Informatics, DSI, with us today. And of course, it's always sponsored by the GAITOR Club and the College of Engineering, AUF. You can find the GAITOR Club here at YouTube. I'm sure if you're here, you already know. There's the Discord, which if you're here, you probably already know. But we also have a Facebook, Instagram, and Twitter. Please follow that when you get the chance, especially the Discord. The Discord is the most active. And the Data Science and Informatics Institute asked me to give a little bit of an introduction today. So they are a community dedicated to sharing ideas and skills related to data science. They offer free workshops to teach analytical tools. Overall, we are students inspired by the fascinating world of data science. Fascinating it is indeed. I totally agree. Again, I'm planning on starting at around 6:30, so this was kind of the intro. We got a lot to talk about today. This has been 3 weeks in the making because the last 2 weeks I've been absent, some would say. But this one's going to be great, and I hope you all enjoy it. So today we're going to start by talking about data frames, and then we're going to talk about how to import data into a data frame, and then we're going to be talking about this cancer data set and what it does. So this first 3 parts are only going to take about the 15 minutes of this lecture. I'm going to be going through really fast. If you guys have any questions, please let me know. And finally, we're going to be talking about helpful Sci-Fi functions, which are like functions that statisticians made in Python that you don't have to make yourself, which is a great resource. I don't see anything in the chat. So I assume all you guys know where to find the GitHub link, the data that you need for this, the breast cancer data set and all that. So if you guys just go up here, you can click on the edit button from the Kaggle, or you can go here. You need to add the Data Csv file. So I'm just going to do a new window. I'm just going to do a new window here. Well, I'll actually download this. Command S, we'll save it as data.csv, and we'll just throw that right in here. Upload. We'll throw that right in here. So I downloaded it, but this is the one from lectures. So if you go to the GitHub, we go lectures, week 5, data, and data.csv. The link to the GitHub is inside of the description, if you guys see it. So we're going to upload data really quick. On Colab, if you guys upload data, it will recycle that data once you're done. So basically what we're going to do is we're going to import, let's go back to, so once you've downloaded all that data, I'm doing this first and then we'll talk about data frames. Just get your setup all working while I'm talking about data frames. To access a data frame as an object, we have to import something called pandas. Normally, when you import pandas, you import it as PD, which in Python is just import pandas as PD, right here, as PD. A pandas data frame is technically a 2D array that is made up of columns, call 1, call 2, call 3, call 4. As you can see, we have 4 columns here, and there's 5 columns here, and there's 4 rows. Okay, and to make a data frame, all you have to do is just say pd.dataframe, some 2D array of data, and then the columns. This array can be pretty much any object. It doesn't really matter. And so yeah, let's talk about what the output would look like. So this is what the output looks like. There's a new column that we didn't put in yet, but we'll talk about that later. Here is Pandas versus Excel, if you guys have never seen Pandas before. So basically this new column that we have is called the index. It basically allows us to know exactly what row we're on. And this index is right here. That's what it would look like in Excel. So if we go back, we can see that this sort of index will keep going to however many max rows we have for each column, which is pretty useful. And as you can see, we have these columns here, the call 1, call 2, call 3, call 1, call 2, call 3, basically like the columns in Excel. And we say calls equals, and boom. So if we wanted to do a calls, this array is what came out, and that's basically it. That's Pandas. It's a table format. So now, what happens if you say df and then you want one of these columns? It returns a series. A series is just a column from a data frame. A data frame is made up of series, and then there's an index array, and then there is a index array here on this side, and then there is a actual value array here. So if we were to get df0, it would give us 6. If we were to put multiple columns into this sort of thing here, it would give us back a data frame because we have multiple series. So yeah, that's basically the idea. If you guys have any questions, let me know. If you guys have never seen Pandas before, hopefully you have. This is a pretty easy concept, in my opinion. I think it's just a table format, which many people have seen before in Excel. So basically, a data frame is just a dictionary of series where you can access each series from a string value or an object value of any kind. But a data frame is just a dictionary of series, but they hold the same index. So every single row has some sort of index, and it holds the same index. And same thing here, we can see that if we were to put an object into this sort of array, so if we were to make this into a dictionary, this is what the dictionary would look like. And again, where's our index? We would just create a new index where the length of the index column is just a range between 0 and the longest length of the column. And so basically that's about it. That's a data frame. Let's see. You can do custom indexing. You can add date ranges. You can say whatever you want the index to be. And when you add things like a date range, you can do cool things where, we can combine tables on dates. You can combine tables on strings, whatever you want. Pandas is a really powerful tool. The only problem is that indexes have to be a type that is comparable, which means that a comparable type has to be greater than, less than, or equal to some other object of the same type. And they have to be kept in order. So there's some sort of order to this thing where we know that 1 is less than 2, 2 is less than 3, 3 is less than 4, etc. That doesn't have to be, but most of the time they're kept in order, and that's to help with performance. There's a bunch more resources on Panda. They even have a thing comparing it to SQL, spreadsheets, R, and a bunch of other things, SAS, data, all this stuff. It's just a basic table structure where you have rows and columns. And if you guys want to learn more about data frames, let me know. I will put more in data frames in the next lecture. For right now, this is about all we have time for, and I hope you guys understand what I'm talking about. So now we're going to go into importing data. We have, let me see. Hold on, I'm pulling up chat right now. Live chat. Here we go. So basically, we have this importing data. We have So if this is an Excel file, a CSV file, it looks like this. We have these CSV files that have read CSV and then the path to the data, which is just any sort of path. We have read Excel, which is just a path to the Excel file, and the sheet name, which is basically the sheet name. And then we have read CSV. If we want custom columns, we have custom columns. Oh, thank you for subscribing, Fatima. I appreciate it. Welcome on. Welcome to the GAITORs. So now that we're talking about that, okay, so we can do custom columns if the CSV or Excel file doesn't have this first row and we want to say exactly what it is. This is actually the CSV file that we're going to be working with today. Looks complicated, but once we put it into Pandas, it'll look a lot better. So now let's talk a little bit about the cancer data set. Right, we have this data set that we got from Kaggle, and there's this code and discussion tabs that you can go and see. So on Kaggle, there's these code and discussion tabs for every data set where you can see code that has used this data set, and you can see examples of how the data set was used. There's also discussion, which is like a forum where you can go and upvote posts, comment on posts, and and join the Kaggle community. So the description of this data set is the features are computed from a digitized image of a fine needle aspirate of breast mass. Basically, these are calculated from an image where they have this this sort of picture of cells really zoomed up, and you can basically take these measurements from that image. And they describe the characteristics of the cell nuclei, which is like the center part of the cell. If I were to pull up like a cell image, like this, it's the center of the cell. And so basically, we get all this data on the cell. There's basic attribute information, which is like ID and diagnosis. And the diagnosis in this case is our target, whether or not it's malignant or benign. And then there's these measured values that come from the image. There's the radius, there's the texture, there's the perimeter, there's the area, there's the smoothness, there's the compactness, there's the concavity, there's the concave points, and there's the symmetry, and there's the fractal dimension. I don't even know what half of those words mean, I'm going to be honest. It beats me. But basically, these are our dependent variables, stuff that we are able to input into our models in order to create something called a dependent variable, which in this case is the diagnosis. Okay? So if you were to imagine this as a function f of x, and we wanted to create f where we have some sort of input, which is the radius, texture, perimeter, area, smoothness, compactness, and we wanted to create a function that produced the y diagnosis, we're basically taking all these different inputs and we're making it into a sort of function. There are 10 total real valued features, which are like sort of independent, but each value also has a mean, a standard error, and a worst. So radius underscore mean, radius underscore standard error, radius underscore worst, sort of, etc. And this is an example of a cell, like a cell, and these little purple things right here in the centers are actual nuclei. That's what we're measuring, and the real valued features, they have each a mean, a standard error, and a worst. So now let's code. We're going to be coding a lot this time around. So basically, since I hope people are following along, you guys said at Data Science that you were following along. I'm going to retype all of my notes, and hopefully this goes well. So basically what we're going to start out with is we're going to import pandas as PD, what we talked about before, and then we're also going to import Seaborn, which is our data visualization library. And so basically we can take this PD, we can take where our data CSV is, we can go over here and copy path, and we can say pd.read CSV, and then we're going to read this path, and we're just going to say that our data is equal to pd.read CSV. This function basically can read to CSVs. You can again, change the columns, do all that jazz. But this data that we have already has columns. We can open it up here. Oh, could not fetch for some reason. Okay, well, let's just say data.head. It already had our columns in here. So we have the diagnosis. So these are our attributes. What we want to, our diagnosis is what we want to produce. We have a radius mean, texture mean, perimeter mean, area mean, smoothest mean, etc. These go all the way through where you have all of them has a standard error, and then all of them have a worst, which is like the least or the most, depending upon what's worst. All right. Now that we're going to talk, now that we've kind of talked about that, let's go over here. So we have one column in here that should not be in here. I don't know why this is in here, but I'm just going to copy that name, and I'm going to say data is equal to data.drop, which is we can drop a row or a column. We just have to say what axis is on. Axis is column, row is 0. And I'll actually add that later. But we can remove this unnamed 32. The axis is 1, and I'll just put this here. Row. Okay, so now we're just going to do data.head again, just to see what our data looks like. And as you can see, after dropping that, we no longer have that last column, which is great. So now that we have this data.head, let's look at the data info on all the columns. And we can see data. Let's just rerun this, because when I drop this, it's no longer there, and it keeps data, so I reset data, which is not good. But as you can see, all of these are float types, which means that this is very ideal for us to use it inside of our models. And as you can see, if you guys can't see it very well, I'm sorry. I can't really, this is about the best that I could do. This is basically all of the columns that we have access to. All we want is diagnosis. We want to change diagnosis to be an int, though. That's our main concern, is what we're trying to do. And what we're going to say for our diagnosis is we're going to say that our data, I can't type. Data diagnosis is equal to the list. Well, we're actually going to say, what we're going to do is we're going to map, and we're going to say lambda, which takes every index in that map. So lambda. So if I were to input, say, an array here of data diagnosis, basically what I can do is just say that for each row in data diagnosis, I go through and I run this function. And I'm going to say 1 if the x is equal to m, and else I want 0. Right? So basically what I'm saying is that I want it to be 1, so I'm going to take these notes here. I want it to be, do this here, text. Let's see, 1 is equal to malignant, and then 2 is equal to benign. Right, okay. So we have malignant and benign cells. Hold on, is there anything in chat? Hopefully you guys are watching. Wait, no, 0 is benign. My bad. 0 is benign. So if we have, say, this data, so if we run this cell, so since we did a map, we have to make this map into a list, which basically is just going, because the map is a generator in Python. So it doesn't have an index technically, it's just a function that runs on something. So we just make it into a list. Now we say data.head. As you can see, now we have 1s or 0s. Try not to run this cell twice because it will give you all zeros, and that's not what we want. So now we're going to go back to data.describe. Oh no. Oh my god. Data.describe. Okay. We're going to describe this data, but we're going to take the .t of it, which just gives us the transpose. Pretty useful function there. So basically we have the count, the mean, the standard deviation, the min, the 20th percentile, the 50th percentile, the 75th percentile, and the max of all of these different things. As you can see, the mean is not 50%, so that's probably not good. Let's take a look at whether or not we have data diagnosis, and we're going to call on that value counts, which is just going to give us the unique values inside of this column here, and it's just going to give us the counts of each of those values. So we have 0 at 357, and we have 1 at 212, which is not ideal. It's not ideal. It's not what we want. We want it to be exactly even for reasons later on, because some of our data, like k nearest neighbors, some of the stuff we're going to be talking about later, requires it to be pretty much exactly the same count. So we're also going to say, so in order to do this, we're going to sort the data. We're going to select a certain amount of each one. We're going to say data is equal to data diagnosis, where data.diagnosis is equal to 1. Did I say? Let's go back up to my notes. Malignant is 1, yes. And then we're going to say then benign is equal to data diagnosis. And then we're going to say when that is equal to 0. All right. So now we have a malignant and benign. So if we just do mal.describe, you can see that the diagnosis, the min is 1 and the max is 1. So we only get ones that are equal to 1. Which is exactly what we want. So if we say malignant 2, but we only want a certain amount of samples of these, so what we can say is mal2 is equal to mal.sample, which is a built-in function for data frames that allows you to select a certain amount of samples. And for this sample, we're just going to say that, n is equal to, say, the minimum between the length of malignant and the length of benign. Right, so now we have this n, where we can just say n is equal to n. So we're going to select n samples randomly, where our random state is equal to whatever. I'm just going to put, what's a good number, Brian?
125.
125. All right, bet. So then we have benign 2 is equal to beg.sample, n is equal to n, and same deal, random state, just to make things a little bit more organized, is equal to 125. So now if we take both of these heads, we can say we have this, and then we want to create this new data frame called df. I'm going to put this up like this. We have this new data frame called df, where we have is equal to pd.concat, and we have these two inside of a two, where we concatenate these two, and we have this df. Now we have this df.head. So we're going to print out this df.head. So now we have two sort of IDs. As you can see, the index changes because we are only adding series, so the series stays the same. There's no real thing, and you can see that it's randomly generating these things because, you know, 223, 87, that's it's pretty random, right? So now that we're here, let's summarize this data. We can visualize this data by, so this takes a while to run, but we already imported SNS, so if you haven't done it yet, import Seaborn as SNS, but I did that in the beginning. We're going to say that our grid is equal to SNS.pairGrid. Oh wait. Right, and we're going to say we want to make a pair grid from our data frame, and we want our hue, which changes the color based off of the value of this column. And the column we want to change the number on is diagnosis. So we want to be able to distinguish between on the graph whether the value ended up being a malignant or benign cell. And yeah, so basically that's about all we have to do to initialize it. We're not quite done yet. We're going to say the map._lower. So you'll figure out what this means later on. But we're going to do, on the lower side, we're going to do a scatter plot. And on the upper side, we're going to do a KDE plot. All right. Okay, I can't type today. And then on the diagonal, we're just going to say that the SNS.KDE plot again, and we're going to say that the line width is equal to 4. Okay, and then we're just going to say we're just going to add a legend to it. Okay, this is going to take a while to run, so while that's running, I'm going to open up the one that I got earlier. And while you guys are doing it, we're just going to look at this. So basically, we have this this sort of X here, and we have a sort of a Y here. So you can see that like 0, 0, it's radius mean. When they're the same, it does this thing. It's on the diagonal, right? So that's pretty easy to figure out. This KDE plot allows us to see, the kernel density estimate, which allows you to see like, oh, there's more orange here. Like this one's higher when it's orange. This one's higher when it's blue. Well, this one's higher when it's orange, which in this case is a, hold on. Forgot what the orange was, to be honest. There should be a legend on here. Yeah, orange is 1, so malignant, and 0 is benign. Well, where's my mouse? Oh, there it is. Okay, so now we're going to go back, and we can kind of see every single sort of variable that we have inside of this. So we have 30 in total, and our output is the changing colors, right? So basically, all of these cells right here, all these orange cells right here, are going to be benign. And then all of these blue cells right here are going to be malignant. All right, so we can kind of see how the computer is going to be able to group these up into their own little groups, right? And this side here, so all you have to do is just switch the row and column, and you get the same graph over here. So this is a kernel density estimate, and this is the actual scatter plot. These are the actual values here. We can see that these correspond to each other. So like this one here would be the same as this one here, etc. You just switch the X and the Y's, or the rows and the columns. So that's a really cool plot to see. This is still going at it. It's going to be going at it for a while. So come back to test train test split. So we're going to be here for a little bit. I don't know how long it's going to be, to be honest, but we'll go back here. So something that really you might have noticed here is that this is in a linear sort of thing here, and then this one is in a sort of I guess you could say like x squared. Well, that's because that the area right here, so this is the area. If we look at the actual formula for the area based off of the radius, it's really just pi r squared, right? So right? So having like something connected to its radius, right? So the perimeter again is just 2 pi r, right? Etc. So technically these variables right here are not independent variables. They're dependent variables because they're based off of the radius, right? We're going to keep them in for now just because they might help weight our actual thing. We'll actually learn about support vectors. These are technically support vectors because they are not dependent variables, but we will learn about support vector machines later, and they are very useful for helping us figure out what the actual plots are supposed to be. Let's see if this is done yet. It's not done yet. Let's just actually, so while we're waiting for that to go, we'll start the train test split. So in order to import train test split, we're going to take something called sklearn, and we have model selection, and we want to import, say, train test split, right? And then we want to say that our x is equal to, so our independent variables, so we want to say that our independent variables are here. Is equal to df, and then we're going to do that dot drop thing again. We want to make sure our axis is 1. And we want to drop the columns. In this one, we want to drop ID, and we want to drop diagnosis. The rest of them, we can consider them to be independent variables, even though we just discussed that some of them aren't, but they can help us with the actual model detection. So now that we're here, we have the y, so we have df diagnosis dot values. So this just gets the actual diagnosis values between 0 and 1. And then we're going to say so I'm actually going to copy and paste this. We're going to say that our x train, our x test, our y train, which is connected to our y train, these two should be the same length. These two should be the same length because they're based off of each other. So for every input, you want to produce this output, and for every input here, you want to produce. No, for every input here, you want to produce that output, and for every input here, you want to produce that output. So we're just making it like if we wanted to say f of x is equal to y, and then we want to produce the y, right? So now that we're done after train test split, now that we've kind of talked about so why would we want to train test split this? Well, because we want to give our model data that it's never seen before in order to test it. So that's how we know our model is doing well, is we know that it should be going, if the y train and the y test are doing well, we want this, if the y train were to produce, if the x train were to produce, if the x train were to produce the y train, we want to create this, we want to map a function, f of x is equal to y based off of these values. But that alone is not enough for us to know that something like that would work. So what we'd have to do is just say that we have to test to make sure that an x that this function has never seen before is able to produce y pretty easily, right? So now that we're waiting for that, we'll wait for this to run. It takes a while just because there's so much data that it has to deal with. But yes, so we're back after train test split. Now that we're talking about that, let's go right into the SciFi functions. So SciFi functions, so SciPy allows us, it gives us a bunch of supporting functions that we can use inside of our code. It's completely MIT licensed. You can use it however you want. It's open source. So first of all, first we're going to talk about normalizing data. Then we're going to go into decision trees, and then from decision trees we're going to go into random forests. And then after that we're going to be talking about k-nearest neighbors. K-nearest neighbors is a really powerful tool. Same as the decision trees, random forests. All these are really powerful tools, and they're all algorithms that SciPy has written so you don't have to, which is really important. We also have the naive Bayes, which allows us to, which is normally used for text, more like a text sort of a classification model. However, it is probability based and it can be used on pretty much anything. So after we talk about naive Bayes, we're going to go into support vector machines. And yeah, if you guys have any questions, please let me know. I see the chat's not really going off right now. I'm kind of just waiting for people to... K-nearest neighbors is goated, indeed. SVMs, yes, support vector machines. So hopefully you guys, in data science, you guys have heard of these before. If you haven't, I will give you guys a little overview today as well, what they are. So first we're going to talk about normalizing data. When we have this data inside of like a data set, right, we have these like normalized sort of functions, right? So we have the normal distributions, we have a bunch of types of distributions. So if we want to like scale the data so it's supposed to be where it's at, so like in a support vector machine, the support vector machine assumes that the mean is at 0 and that the standard deviation is 1. So it basically assumes that the data fits this graph. And when we scale the data, we basically want to multiply the data by certain numbers or add or subtract in order to like on the entire data set to move it so it fits this graph. And to do this, we call standard scalar. This is called normal distribution. I'll actually go through and show you guys how the scaling and everything works on the normal distribution. The location of this, the center, is the mean in this case, and the scale, which we will talk about later, is the standard deviation. Right, so let's hop into Desmos. As you can see, we have the mean 0 here. If we move this mean around, I'm actually going to animate it. If we move this mean around, it moves our center. It moves it left and right, and we can see that as our mean is moving up and down, the center is moving up and down. So if we move this back to 1, let's move this back to 0, we can see that our normal right here, if we play the standard deviation, we can see that our graph goes up, down, and then the lower and lower it goes, it starts to go up really high, and it goes down. So that's basically how we can scale our normal graph. But what we want to do is scale our data so our graph looks exactly like this graph, where m is 0 and the scale is 1. There's different types of scales as well. There's a min-max scalar which we can use, which scales the data linearly between -1 and 1. It's not normalized. It doesn't fit the data like it should. However, that is a very powerful tool and is used a lot. There are a bunch of other methods in this class as well. You don't need to just use these. These are just the most common. All right, so now that we've talked about, I drew a red line here for the mean. Hopefully you guys understand that. So now let's code. How would we implement this? It's line weight. My bad. We're just going to stop this, actually. We're just going to stop it one time. Yeah, we're just going to go like this. One time. Restart. Restart runtime. Yes. We're just going to run through all these again. If you guys are just joining in, welcome. Appreciate you all coming. Again, I'm looking at the chat. Hopefully you all are understanding what's happening. So now let's talk about decision trees. Oh wait, never mind. We're talking about scaling data. So over here I have, let me actually show you guys this. I have a bunch of data on what the normal distribution is on the GitHub, but we're not going to talk about that today because we don't have time. I only have about 25 minutes left, and we're just now getting started, basically. So I linked the Desmos demo if you guys want to go and play around with the sliders and everything and all that jazz. So basically, what we're going to do is we're going to import this from sklearn.preprocessing, import a standard scalar, right, and then from sklearn.preprocessing. Oh wait, I actually don't use this, but we can import standard scalar, or you can import min-max scalar. The only difference is that this would be min-max scalar, but we're just using standard scalar for today. And basically, we want to create this object where we have a standard scalar here, and then we want to say scalar, and then to make it fit our data is equal to scalar dot fit, and we can fit this data to x underscore train. Right, so we have this data x underscore train, and we want to say def input, and then we're just going to say x, and then we're going to say return. So we're going to we're defining a function scale input, and we're just going to return scalar dot transform, which basically runs so it fits this train data for each column. So if we had like x train in the 0 column, it would be like all normalized, in the second column all normalized, in the third column all normalized, etc. So I'm just creating this function that'll transform x, and then I go here, and then I say x underscore train is equal to scale input, and then the x underscore train. Okay, and then we have x underscore test, can't type today, is equal to scale underscore input, and we're going to do x underscore test here. All right, so we're going to call that should work. Okay, so now that we have x train, so let's just look at these real fast. We have x train, which should be a 2D array of values, and they're scaled accordingly based off of where their distribution should be on the normal graph, which is great. It's all fine and dandy. As you can see, when I fit it, I only did the x train. That's very important because we want it to never see the test data before it's scaled or before it's run. So now that we've done some standard scaling, we can go back here and we can talk about decision trees. So decision trees are basically just grouping data in a way using statistics. We don't really have time to talk about how they do it today. However, I found this really cool GIF that I think shows how it does it really well. It basically separates things into groups based off of the optimal place to put lines, or in the optimal place to group things. The root node is the actual node that has all the children, and the leaf nodes are nodes that are at the end and don't have any children, and these nodes produce an output, whether it's 0, 1, yes, no, malignant, benign. It doesn't really matter. They produce an output. One of the great things about decision trees is you're able to combine numerical data and Boolean or categorical data, like yes or no data, into one tree, which is very useful and can be used quite a bit. One of the great things about decision trees is that they're very intuitive to work with, and you can actually see what the tree is doing and separating it by, which is really useful. And basically, a random forest is just a bunch of decision trees, or n decision trees, whatever you want to say, n estimators. And then they all create a vote, and then whoever has the majority vote wins. Okay, so that's basically what a decision tree in a random forest is and how it works. If you guys have any questions, please let me know. I would love to answer some about this. These are very, very powerful. So now to implementing it, all we're going to do is we're just going to say from sklearn.tree, we're going to import the decision tree classifier here. So we want to make sure that it's a classifier, because all we're doing is saying whether it's a yes or no. If we were to be doing a regression, like something that we wanted a numerical value out of, we would want to say decision tree regressor. But since we're using classifier, we're just going to say classifier is equal to classifier, can't type today, decision tree classifier, and then we're just going to want to say n estimators. So the number of, we're going to want to say max depth is equal to 5, just so our max depth is like actually good, and we don't go too far. And then we're going to say, we can actually say what our max depth is. So if I were to go here to the documentation for it, we can see there's a bunch of different things that we can do for the n estimators or max features. We can do auto, square root, log, none. This is important. We can change that later, but that's very important, the max depth. And now we have the classifier dot fit, and then we have x underscore train, the one that we so our lowercase x is the one that we scaled, right? And then we want to train it to our y underscore train, right? So we call this our classifier with a max depth of 5 is all ready to go. And so basically we have this thing called a confusion matrix, which you can see here, that generates something called a that generates this sort of matrix type thing where the diagonals are correct and the wrongs are the wrong guesses. So in this case, where it would be 0, the rows would be what it predicted, and then the columns would be what it was actually supposed to be. So it's just an easy way for us to visualize how our actual model did. So if we run this and we get our confusion matrix, we can go from sklearn.metrics. We're going to do import confusion matrix. Again, all these functions are already made. So we're just going to say confusion matrix is equal to confusion matrix. And then we're going to say y underscore test, so what we wanted to be true, y true. And then our predictions, which we're just going to say classifier dot predict. And then whatever our x underscore test was. Okay. So now we're going to take this and we're going to say sns.heatmap, and we're just going to generate a heat map of the confusion matrix. All right, using SNS. So as you can see, we have this confusion matrix coming out, but we want it to be annotated. Is equal to true. We want to change our color. So color map is equal to Verdis. I like this color map. It's my own personal preference. I think it looks good. And then we're gonna actually, we're gonna add, we didn't need to do that. So basically, as you can see from this model, this decision tree classifier, we were able to get 50 out of 106. We got 96 of them right, which is a 96 out of 106. 90% accuracy, which is pretty good, if you ask me. I think that's pretty good. And then we're going to do the same thing. So now that we've gotten like a 90% accuracy, we can actually increase this max depth if we want. We can make it a little bit higher, but as you can see, like the more we increase it, the like it doesn't really help like that much. Like it's not gonna like. I'm sure we got one better that time, but it's really not gonna help that much. But basically, we're just gonna take these import statements. So we have matplotlib.pyplot as PLT. So this is like this is matplotlib that we're going to use, and then we just use this thing called export underscore. Wait, no, we don't need this. We're just going to use this thing called plot underscore tree that takes, and then we're going to say plt.figure fig size is equal to. We'll just do like 25, 10, something like that. I don't know. And then we're just going to say that we want to plot underscore tree. And the tree that we want is our classifier. And we want it filled is equal to true, which just fills in the squares we're going to get rounded is equal to true, just to round up the circles. And then we want our feature names. So to this classifier right now, the feature names are just an array of like 0, 1, 2. But what we want is to make that array into the features that we want it to be called. So we're going to take a variable called feature names, and we're just going to say that it's going to be the df.drop. So drop the actual feature names that we want to drop, so like ID and diagnosis. Axis is equal to 1, don't forget that. We can see our feature name is equal to that, and then we want to get the columns from this. So we're just going to get all of our columns, and we're just going to copy and paste this variable right in here, and we're going to get our feature names. So now we can plot this tree, and it's going to generate a tree, and you can see that the concave points worst was the best half point. We have the Gini, we have the number of samples that went in here, so 318. So it splits it in half, and then it goes to the next one where it says area worst or perimeter mean, etc. So we can actually go in and see what this model is like cutting in half to use. Pretty cool, right, Ron? Mm-hmm. Pretty cool. And we can use these parameters, so we know that like concave points worst is like the worst, is like the most, is the hardest one, etc. So I think that's pretty cool. I think that's a really cool feature that they have. And since we also talked about random forest, I'm just going to go in here and copy and paste this in. You guys probably don't need to do this. It's kind of the same deal. Random forest classifier. So the n estimators is 5. You can also do a max underscore depth as well, but we're just going to let that slide. We're going to say the random estimators, and then we're just going to make that equal to model, and that would be fit. And same thing here. We want to use the confusion matrix to figure out how well this is working. We have y-test, classifier, predict, etc. And we have the heat map. Okay, so I don't have a lot of time. I kind of went fast on this, so I'm going to have to kind of copy and paste things in here a little bit more than I thought. But now that we're here, let's talk about what a k-nearest neighbors is. So we're going to draw this out. I have an example graph here. Let me go like this. So if I have like a graph that looks like this, and I say have an unsuccessful point right here. So if I wanted to do like this, draw. If I wanted to have like an unsuccessful point here, right? What this algorithm is going to do is it's going to count all the nearest neighbors here. So we can see all these nearest neighbors, and so say our k is 5, and it's going to give us the distance. Drawing with my mouse right now, and it's going to tell us which point is which. So it's going to tell us the classification. So we're going to take that, and we're going to kind of take this function that runs k-nearest neighbors in here. We're going to say get neighbors, and instead of doing this for now, we're just going to print out each mean right here. So if we go right here and we do the y-index, you can see that we get, so if our k-nearest neighbors was 5, we get 5 of the nearest neighbors, right? Which is really cool. It tells us what the actual classification was for each indice. So we can see like this one was 1, this one was 1. This one's a little bit less easy to figure out because it could be a 0 or a 1. 1, 0, 0, 0, etc. So if we do that and we take the mean of each of these, then we can kind of get like an average of what it was. And since we're using 5, we can just take we can round it up or down, and we can get our predictions. And yeah, that's basically it. That's how I did k-nearest neighbors. Go run through and see later on what's going on, but for right now I'm going to have to kind of rush through this because we don't have a lot of time left. So now we generate a confusion matrix of the same thing. As you can see, we did quite a bit better. We have only 1 wrong in this area and 5 wrong here, which is now a 6 out of 106. Oh, 90, I guess, well, a 94.3% accuracy, which is pretty good. That's pretty good. So now that we've talked about k-nearest neighbors, and we kind of drew it out and how k-nearest neighbors works, let's forget. Okay, so I'm back here for naive Bayes. basically what naive Bayes does is it takes the actual likelihood of each column. So if the column has a likelihood, so this is a lot easier with an example. Naive Bayes is normally used for classifying spam. It's a very naive approach to distributions and probabilities, but it did kind of set the standard for like figuring out like spam emails or classifying text stuff. So basically, an example here would be if there are 3 categories of fruits, long, sweet, yellow, and total. I'm actually going to pull this up for a reference as well while we're talking about it. Let me go here. On Monday, week 5. So I'll pull up this table reference here. And you can see as we're going along what this table is. So we have our examples. We have the banana, orange, and other. And we're told that there is a fruit that is long, sweet, and yellow. And our job is to find the category with the highest probability. And that category with the highest probability is the winner. So the probability that it would be a banana, right, would be the probability of it being long divided by the total number of bananas. So it would be like 0.8, right? So let's go on to the next thing. And then what we'd have here, what we'd have after is that we'd have the sweet banana right here. If it's sweet, there's 350 out of 500 of those, so that's 0.7. And then we have yellow, which is going to be 450 out of 500, so we have 0.5. And so the probability of that is divided by the probability that the entire data set's data is what should we call it? So 400 out of 500 out of 500 out of 1,000 were long. 650 out of 1,000 were long. So 350 out of 1,000 were long, and so on. So basically, the idea is we just multiply these together and we get the probability that it is a banana. We do the same thing. So this is what our probability was. Now the probability of an orange is 0 because 0 on the numerator here, 0 times 0 would be 0. So the numerator, no matter what, is going to be 0 because there's nothing that an orange said was going to be, what should we call it? There was no orange that has ever been, long. Okay, and so the probability of other, so we go through the same steps, we just multiply the probabilities, and we get that other has a probability of 0.01875. And so finally we say that it is a banana because the highest probability from our math says that it is a banana. So we don't have to do this ourselves. We can just use the functions that come in sklearn. So naive Bayes like this. We use a Gaussian naive Bayes, which uses a normal distribution. There's a bunch of different types of distributions that you can use with this. You can use Gaussian, you can use multinomial, you can use complement naive Bayes. I really suggest you guys go in and look at all these. Categorical naive Bayes might have been a good thing for us to use this time around, but we used Gaussian naive Bayes because that's the most common. And so we have this model fit, the Gaussian naive Bayes. Again, I'm sorry, I'm not typing this out. We don't have enough time. And we get this confusion matrix at the end, where again we have about 90% accuracy, which is pretty good. Not 90% accuracy is fairly decent. And finally, now that we're here, let's talk about support vector machines. So say we have a nonlinear data set like this, and we want to find a way to categorize this data in a linear way. Well, look no further than support vector machines. Basically, what we are going to do is we're going to generate a dependent variable, something that we're going to scale up all these values, and we're going to add another dimension. And this new dimension that we added here, for example, would be z is equal to x squared plus y squared. So it's a dependent variable. But all what we can use this for is this. We add this z. So imagine if this was flipped on the top, and you can see like a z. Okay, and we're gonna put a line here. So basically what's happening is we're putting a line in between the two data sets, and we're making that into a plane essentially. And then from the plane, we can take where our plane hits our function in the z, and we can create a circle around it, which is called, in this case, a hyperplane, which is also a regression. So here's a cool visualization I found. Hopefully y'all can see this. So let's see, how do I? So we'll go here. So you can see, as you can see, this was the same data set that we had, kind of, where it's like a circular data set, and it's going to lift them all up. So it's multiplying these. So this would be like x squared, y, z is equal to x squared plus y squared, etc. And then it's just going to take a plane, slice the data in the best way it can. So it's going to take a plane, slice the data in the best way it can, take this equation where they intersect, these two planes intersect, and it's going to create a circle around it. Basically, that's going to be our new classification. Everything inside of this circle becomes that classified, and everything outside the circle is the other classification. So yeah, I thought that was a cool visualization. Yeah, I hope you guys like that one too. But yeah, let's go right into visualizing it. This is our last code for today. So basically, all we have to do to import this is just say sklearn import svm, and we're going to go through and we're going to say that the kernel, so svc in this case would be a support vector classifier, and our kernel we're going to use rbf, which is just the kernel is the function that we're using to scale our other values, and in this case is rbf. Our gamma is 0.1, which is like our sort of how much we want to rotate it sort of every time while we're testing, and then our C is 10, so we have we only look at 10 columns or n dimensions at the same time. So we model.fit all this stuff to that, and then same thing, all it is just we're creating this model object, and then we're fitting this object to our xtrain and xtest, pretty common stuff, and we're generating a confusion matrix based off of this. And this one did really well, only got 7 wrong. And yeah, that's basically support vector machines. I went really fast and we're out of time. However, I do hope you guys are understanding that I don't have a lot of time on these. So if you guys have any questions, please let me know in the chat. I'll stay here for a couple more minutes. Yeah, so again, let me go back to DSI. So DSI wanted you guys to hold on. DSI wanted you guys to go to their link tree, join all their stuff. Again, they are community dedicated to sharing ideas and skills related to data science. We offer free workshops and teach analytical tools. However, we are students inspired by the fascinating world of data science. I agree. It is very fascinating. But yeah, I hope you all enjoyed it. I hope you guys subscribed. And yeah, if you guys have any questions, let me know. Hopefully, I didn't go too fast. Well, I probably did, but thank you all for coming, and have a great day. Bye.